we want to evaluate the triple integral over the region E, where the region E is the solid region enclosed by the paraboloid z equals 3 plus x squared plus y squared, the cylinder x squared plus y squared equals 2, and the xy plane. Let's begin by looking at the region E in space. So the region E is a solid region here, bounded by the paraboloid graphed here in blue, the cylinder graphed here in purple, and the xy plane graphed here in yellow. Because this region is bounded by the cylinder, it's going to be easier to use cylindrical coordinates rather than rectangular coordinates to evaluate the triple integral. If we look down on the xy plane, we can see the xy trace. Notice how the xy trace is this circle, x squared plus y squared equals 2. So going back to our work, to write a triple integral given in rectangular coordinates, in cylindrical coordinates, we have to write the integrand function f of x comma y comma z as a function of r theta and z, and differential v is equal to r dz dr d theta. So using cylindrical coordinates, just like polar coordinates, we're going to have an extra factor of r in the integrand function. So starting with the given triple integral, to write this in cylindrical coordinates, e to the z is already a function of z, so there's no conversion to perform with this function, but we are going to have an extra factor of r in the integrand function. So the integrand function is going to be r times e raised to the power of z, and then we'll use the order of integration given by dz dr d theta. And now we need to find the limits of integration for z, r, and theta. Well, the solid region of integration is bounded below by the xy plane, which has an equation z equals 0, and above by the paraboloid given by z equals 3 plus x squared plus y squared. But we need to express z in terms of r and theta, so we'll perform a substitution for x squared plus y squared. X squared plus y squared is equal to r squared, so the region of integration is bounded above by z equals 3 plus r squared, which means the limits of integration for z are going to be from 0 to 3 plus r squared. And now to help us find the limits of integration for r and theta, we'll take a look at the xy trace. The xy trace is going to be the circle here, given by the equation x squared plus y squared equals 2, which in polar or cylindrical form would be the equation r squared equals 2, or r equals plus or minus the square root of 2. So the xy trace is this circle here. So using this circle, the limits of integration for r are going to be from r equals 0 to r equals the square root of 2. The limits of integration for theta to trace out this circle are going to be from theta equals 0 all the way around the circle to theta equals 2 pi radians. So we have from 0 to 2 pi radians. And now we first integrate with respect to z, treating r as a constant, and therefore the antiderivative is just going to be r times e to the z. And now we need to find big F of b minus big F of a by performing substitution for z. So we're going to have r times the quantity e raised to the power of 3 plus r squared minus e to the 0. E to the 0 is equal to 1, so distributing, the new integrated function is going to be r times e raised to the power of 3 plus r squared, and then minus r times 1, so minus r. And now we integrate with respect to r. Notice how to integrate this first term with respect to r, we do have to perform u substitution, where u is equal to the exponent of 3 plus r squared, and therefore differential u is equal to 2r differential r. So if we divide both sides by 2, notice how 1/2 differential u is equal to r dr, which means we can think of r times e raised to the power of 3 plus r squared differential r as 1/2 e to the u differential u. So when we find the antiderivative of this first term, we're just going to have 1/2 times e raised to the power of 3 plus r squared, and then we have minus the antiderivative of r with respect to r is going to be r squared divided by 2, or 1/2 r squared. And now we need to find big F of b minus big F of a by performing substitution for r. So when r is equal to the square root of 2, we're going to have 1/2 times e raised to the power of 3 plus the square root of 2 squared is just 2, minus 1/2 times the square root of 2 squared is just 2, minus, when r is 0, we're going to have 1/2 times e raised to the power of 3, and then just minus 0. And now simplifying, let's write this as 1/2 e to the 5th. We have a minus 1 here, but we also have minus 1/2 e to the 3rd. Let's write minus 1/2 e to the 3rd first, and then minus 1. Notice how each of these terms are just constants. So now when we integrate with respect to theta, we're just going to have this constant, 1/2 e to the 5th minus 1/2 e to the 3rd minus 1 times the antiderivative of theta. And finally, performing substitution here, we just have the constant 1/2 e to the 5th minus 1/2 e to the 3rd minus 1 times, we just have 2 pi minus 0. So the exact value of the triple integral is going to be 1/2 e to the 5th minus 1/2 e to the 3rd minus 1 times 2 pi. Or as a decimal approximation, this comes out to approximately 396.8699. I hope you found this helpful.